Hello, my name is Conor and this is an overview of my project called Job Scheduling Algorithms for the High Performance Computing Systems. Since this video is subject to time limits, I will only highlight the main ideas, but if you would like to read in more detail, my final report will be published on the Summer of HPC website. To begin this presentation, I will give an overview of the goals of the High Performance Computing System Simulator. Then I will look at the implementation of the algorithms in the simulator before discussing workload job traces. Next, I will talk about some of the job scheduling and task mapping algorithms. Penultimately, I will go into the details of the backfilling algorithm and how we score its components with a heuristic approach, before finally discussing some work for the future. So to start, the first question to ask is, why do we need a HPC simulator? Well, HPC systems are expensive and in demand, so in order to avoid using up precious node resources, a simulator of a HPC system has been developed. The goal of this project is to use the simulator to test different job scheduling algorithms, to assign jobs to nodes so that we can maximize the number of jobs completed on the HPC system in a certain period of time. Equivalently, this also means to minimize the time for which nodes are left vacant in the same period. The HPC simulator uses multi-dimensional arrays to represent the nodes, and if they are busy or vacant as a function of time. This diagram conveys a nice way to visualize this. Every job is specified by its ID, size, arrival time, requested time to run, application name, application arguments, queue name, and arguments related to job scheduling. There are three main modules to the simulator. They are job submission, job scheduling, and job execution. The job submission module contains the workload models and workload archives. Testing different synthetic workloads gives a more rigorous approach to analyzing algorithms. We will discuss this more in the next slide. The job scheduling module contains the job scheduling and task mapping algorithms. Task mapping algorithms determine which compute nodes to run jobs on. The scheduling algorithms are run in a separate simulation process. Finally, the job execution module contains the simulator's communication and computation models. Finished jobs are placed among all finished jobs for statistics collection. Our job submission module is served by parallel workload archives from logs of job traces and Archer. Furthermore, more variety for testing different algorithms can be gained by using workload models. For example, plotted below is one of the first such models published by Calzarosa and Sarazi. The job arrival process is a function of the time of the day. The dip that occurs in this plot mimics the lunchtime break in the day. From the equation, it is clear that the formula has been generated by multi-parameter regression. But this model is underspecified. It does not give job runtimes or specify the number of nodes for each job. Many current models do, and they come with written code. Initially, the simulator only had the first come, first serve algorithm. In this project, we strive for better performance than first come, first serve. So let's look at some other algorithms. First off, the score-based priority algorithm, which sorts jobs according to scores where we incorporate a fair share scheduling weight to adjust the score based on the total number of compute nodes requested by the user, their number of jobs running, their recent history, and the fraction of jobs completed. Next, we have the multi-queue priority algorithm. It incorporates numerous queues with different levels of priority, and there are certain conditions required to be in each queue. Finally, we have backfilling. Here we opportunistically run low priority jobs when insufficient resources are available for high priority jobs. That's our list of job scheduling algorithms, which sort the order of the job waiting queue. The scheduling algorithm runs on job events when a job starts, finishes, aborts, or arrives, and if there are no events in the past 10 seconds, it runs anyway. The task mapping algorithms determine which compute nodes to run the job on. The goal is to minimize the communication overhead and reduce cross-job interference. The worst case scenarios taken is random. Round robin keeps the nodes in an ordered list, and when a job ends, the node is appended to the list. Over time, the fragmentation of the list becomes significant, and the communication overhead drastically increases. The dual end algorithm works by setting a threshold value for time which groups every job into either short or long. Short jobs search for unoccupied nodes from one end of the list, and long jobs search the other end. In the backfilling algorithm, each job has a priority value P of j, with the way queue being ordered in terms of the highest priority. The priority is the sum of the 5 different heuristics. The first one, minimal requirements, specifies details like the number of nodes. Then aging helps avoid job starvation and is shown in detail on the right, where age factor is a multiplicative factor of choice. Deadline maximizes the number of jobs terminated with by a certain deadline. License heuristics gives a high score to jobs requiring critical resources on nodes, such as NVRAM, which hasn't yet been implemented in this project. Response minimizes the wait time for jobs with the shortest execution times by a boost value, which is the backfilling component of this algorithm. Some possible routes of further work for this project are to create a visualization for the simulator, create experiments to test and analyze the performance of the algorithms, and to incorporate using NVRAM technology into the algorithm. Finally, I'd like to thank my supervisor Nick Johnson for all the guidance through the 2 months. I'd like to thank EPCC and the NextGen IO team for the use of their facilities and their friendliness. Of course, I'd like to thank Prates for giving me a place on this Summer of HPC program. Goodbye, and thanks for watching.